So I'm going to be talking about, first of all, maybe in this room, I hope everybody is familiar with the complication of embedded testing. But for some of you that might not be, I'm going to talk a little bit about what's the issue with embedded tests, and in particular, embedded functional tests. Then I'm going to discuss the model that we're proposing or solution for automating the analysis, discuss some preliminary results, and then discuss about a little bit about future work. All right, so what's complicated about test results? I mean, it's just pass-fail, right? Well, when we talk about embedded, even the simplest, boot the board test, it's a little bit, there are more requirements than the traditional, software test that you might be more familiar with. So first of all, you will have to have a build machine to build the images. You will need to have, most of the time, some sort of host server that will connect to the device under test and control it and provide services like, I don't know, TFTP to download files or NFS to run the file system. Of course, you have to have good USB, good USB hub, otherwise you might have serial connectivity issues and Ethernet problems. I mean, the list goes on and on. Even, I'm just talking about a simple boot test, right? And of course, your logic of, the sequence of the commands to boot the board and checking that it booted and so on have to be correct. Now, we start getting a little bit more complicated and then talk about beyond booting the board and talking about functional tests. So here I'm showing, I mean, the picture might not be, I just took it with my cell phone in one of the setups in the lab, but I'm trying to describe that when we talk about embedded functional tests, the setups gets more complicated really fast. In this case, here at the bottom you can see this is not the device under test or EVM, this is actually a multimeter, and it's connected through this ribbon cable to measure power in different power domains in the board. We also have these two black boxes here are devices to measure. We have camera sensors, so through that guy we can control patterns that the camera sensor will see, and then we can validate if the sensor is working properly or not by comparing what is capturing through a golden reference. We have USB, well in this case a thumb drive, we have audio, loopbacks, we have some cables here to emulate GPIO inputs. We have an HDMI tester device here, but the bottom line is like, in the previous slide, I just showed the simplest setup just to do boot. Now we start adding all this test equipment to do functional testing, and things start getting more complicated. And now things can get even more complicated when we start talking about multiple of the setups that I have in the previous slide. Now I have two of those connected to each other, and so we have two what we call these two are the devices under test, or EVMs we call it. And these two little boards here are just helpers, boards that we call automation interface, that they control multiple things on the EVMs like power, boot mode switches, resetting the board, measuring power, etc. And in this case, you can see this cable, this ribbon cable here, connecting the two PCI boards, cards. In this case, one board is acting as a PCI root complex and the other as the endpoint. But my point is that, now complexities start multiplying, right? And this is the issue with running functional embedded tests, that many things can go wrong, right? Yeah, and if there is this kind of if you have a single point of failure in the whole chain, the whole test case will fail. And then you have to figure out, okay, one went wrong by my functional test is not working. And it might be that, there was a kernel change that actually broke the system. Nothing wrong with the setup or the test logic. And now imagine having hundreds of these complex setups in the lab. So we have, in our lab, we have, I don't know, about 60 or so test racks. We manage around, or my team manage around 30 of those. We have hundreds of devices under test. We run thousands of functional and performance tests every day. The list, as probably same situation for all of you, is always growing, you know, more devices, more operating systems, more products. And, you know, on top of all this scaling explosion, as I mentioned before, we have the complexity of having multiple potential failure reasons, right? There might be a test case might be failing because there is a known bug. We have a bug, we know it, and yeah, it's causing you know, that particular test case to fail. There might be some issue with the setup itself. Maybe, I don't know, USB cable got loose. Or it might be an issue with your test logic. Maybe somebody did a patch in the latest version of the test script that broke. Or maybe you tested or you developed it on one platform and now you're running on a different platform and it doesn't behave quite as you expected. Or, of course, there might be new bugs, right, introduced by software you're testing, the new software images. All right, so the first part of the presentation, I just wanted to make you aware of the problem we're dealing with. Any questions on that? Okay, so I expect everybody's familiar with functional embedded testing problems here. So now I'm going to move to the proposed model. All right. So in our system, we're essentially collecting data from two places. We're collecting data from our, you can think your test logs or whatever is your mechanism to store test results, or your database, whatever system you have a database or some file server that contains all your test results and test logs and so on. So that's one of the input. The other input that we take is we also connect to our bug system. In our case, we use Jira, but you might use Bugzilla or whatever it is that you're using. The system also connects to that bug database system. And then there are cases where when we run a test, if the test case passes, then we don't need to run it through our model. I mean, pass is a pass. We just classify directly the test result as a pass. The other easy case is if it is a known problem. If we run a test and it fails and we know that it's associated with an existing bug that has not been fixed, then we will go ahead and classify that particular test results into the non-bugs bucket, right? Now, the other three potential classifications or buckets are test issue, setup issue, or a potential new problem in the hardware software you're testing. And for those three buckets is the one that we need to run our model. And we're going to take inputs from two different places, from the test logs and from what we call here the execution history. And you might ask, why using the execution history? Well, it has been our experience that the execution history matters, and I'll give you an example. Let's say you have a test case that if you look at the last 10 days, it pass, fail, pass, fail, pass, fail, pass, fail. So it's kind of flipping between passes and fails. Does it tell you something? We believe that that information does tell you something. In our case, we believe that it might point into perhaps a deficiency in the test logic. Perhaps your pass criteria is too strict. So we believe that that history of execution is important into doing the appropriate classification. It's not only about, oh, I'm going to look into the last result and see what the output is. I mean, that's important, but in addition, we want to combine that with this execution history aspect. So we have these kind of two sources of information. All right, so going a little bit more details into the model. So I'll probably, just in the interest of time, I'll probably describe it just using this picture. So as I mentioned, we take into the model, we have two sources on the input, our test logs or execution notes, and our execution history. So for the top part, what we're trying to do here is that we will process all the logs or your execution notes, and we will try to determine, in our model, we're trying to extract the 2024 most significant tokens of your test logs. We took, in our case, we took some simplifications. We are not processing the whole boot log. we're processing in our execution nodes. What we're using part of the test logs. I mean, and we're using also part of the debug information that our system prints. So we're combining a little bit of the actual data coming from the device under test with some information coming from our test framework that kind of provide details about what's going on. And then we strip those logs. I mean, there is information there that you really don't want to consider, like dates or name of machines. And so you strip that data or clean it up, and then we run it to a TF-IDF algorithm. Essentially, what this guy is doing is called term frequency inverse document frequency. And what he's doing is he's trying to figure out which are the relevant tokens, which are the most important 1024 tokens in our model. I mean, this is configurable, but in our case, we use 1024. You are, depending on your problem and the type of execution nodes you're using, you might want to change that. But essentially what it's doing is if there are terms that appear in all the documents, then they are probably less interesting, right? It's something that is happening all the time. Maybe, I don't know, your root, right, the word in your root, in your problem. I mean, is that really interesting? Probably not. So the inverse document frequency will essentially score those tokens less because it's happening across all document sets. And the term frequency is trying to raise the weight of the documents that are somehow important. So at the end, you're kind of combining these two and extracting the 1024 most important features. And then we combine that with the 1024 execution patterns. These execution patterns come from the last 10 runs of the test. So essentially, we just take the last 10 runs of, imagine we have zeros and ones representing pass and fails. We convert that sequence into a 1024, we encode it into one of 1024 potential values. So that way we have a symmetric system where half of the inputs are associated with the tokens of the logs, and half of the input into the model is coming from the execution history. We're just trying to balance it out. And then the outputs of the model are, as I mentioned before, we're using this to classify what we call hard failures, or failures that are not known, they are not associated with existing problems. So if you run a test and you pass, your execution nodes and you pass your last 10 runs into the neural network, the output of the neural network will be a label that says, based on the information you're telling me, this test failed because it's a potential problem with the new software, or it's a problem with the test script, or it's a problem with the setup. And I'm not going to describe, I mean, you're familiar with all the potential setup and test issues might happen. So in the interest of time, going to move forward. All right, this is important. We have thousands of test results. And I don't know if you know, but we're using what is called supervised learning, which means that we have to label each data to train the model. We have thousands of results, right? I said we run thousands of tests every day. We wouldn't have a team if I asked them to, hey, let's classify all these results manually. So we have to come up with a heuristic way of pre-classifying the results, and then we can train the model using that heuristic classification. Of course, the heuristic classification is not perfect, but what we're trying to do is get us to a point that is somehow close to the actual model, and then I'm going to explain how we'll retrain the model to get it to be better and better with time. And for the heuristics, I mean, there is some logic that we know when, or there are patterns that we can identify. And sure, if you look at your test logs, there are patterns you can identify as well as something being a setup problem. So we just have some hard-coded patterns. Hey, if you see this in the logs, this is a setup issue. So classify that as a setup issue. There are, for the test issues, there are also some patterns that we know this is a test issue. For instance, if there is an exception being raised, and we know, we shouldn't be, I mean, at least in our framework, we tend to raise exceptions when we want to highlight an issue with the test script. So we can detect those, and also important here, based on the execution history, we can also mark something as a test failure. For instance, if we have this flip pattern, we will, in the heuristic classification, we'll say classify this as a test issue, because this is something we want to highlight. Why are we passing and failing this test all the time? I mean, if you have a good test case, it should either pass, or, I mean, ideally it should pass all the time unless you have a non-problem, right? The other problem, if it's failing all the time, we will also highlight that as a test issue, because it's either a problem with your test script or you should open a defect, right? And in that case, it doesn't come into this model. It goes into one of the first buckets of non-bug problem, right? So, and of course, if in the heuristic classification doesn't match any of these two, then we say, okay, this is a potential software problem. So we'll put it in the last bucket. All right. So I said we use this heuristic classification to pre-train the model, but our model, after we train it, is going to be as good as the heuristics that we apply, which are not perfect, because there is more complexity involved in the system. That's why we're using a neural network. So that's why in our test reporting, for every report or every classification, you have the issue to reclassify. So you have the button to say, hey, I know the model is classifying this as a test issue, but you know what? This was a setup issue. So whoever is looking at the results can click the button, and it will go into a table that says, oh, okay, this actually have to be reclassified, and periodically we retrain the model, uses the entries on that table, and then we clean the table, because we already retrained the model based on those errors. All right. So this is, if I put all this in one complicated slide, you can see, so we run a test and we have the inputs. We have stuff coming from our test database. If a test pass, it goes directly into the pass bucket. If it fails, then it comes here. We also query our bug system. If there is a non-bug associated with this test case, it's also a simple case. It goes into the active bug bucket. If there is no non-problem associated with that failure, then it comes into the neural network model. So we extract the inputs, as I mentioned earlier. We run the neural network, and then we get one of these three classifications. At the end, we have the report, and if there are errors in the classification, the tester, reclassify that, and we retrain the model. So the goal here is that the model gets better and better with time, because it's learning from the errors it made. All right, so that's all I have explaining the model. Well, I'm not going to ask, I'm sure you might have a lot of questions, so if I ask for questions now, I might not finish the presentation. So at the end, if we don't have time, we can talk outside, or let's see. So let me go into preliminary results. All right, so here I'm comparing, we ran the model on Linux and Android and TI real-time operating system. And as expected, I mean, we're using a neural network, and we really, it's probably one of the most simplest implementation of neural networks out there. I mean, we only have 2,048 inputs and 3 outputs, and really it's not that complicated. So as expected, this guy, the neural network, was able to train and learn from our heuristic classifications, and you can see here that the precision and recall are pretty good. And confusion metrics, I mean, it's almost making no mistakes. I mean, so it's essentially, it learned really well it's able to, I believe when we did this, we took 75% of the samples to train, and then the other 25% of the samples to test our model. And we can see that we get pretty accurate results for that heuristic classification. So at least it's as good as a heuristic classifier. All right, so here I'm showing some of the results pages. This is the one that is kind of the summary page. You can see the 5 buckets. And we made a decision, we want to have everything in a single page. Okay, I don't want to have to click and go into 10 different, no, everything has to be in a single page. And we want to have sorting and filtering across all the fields in all the buckets. So it's very easy to do triaging from a different web page. And it's very fast because we're using React. So it's all in your browser. You don't have to go somewhere else. It's really, really fast. This is what the results. So if if you expand, these guys, then it opens more data about the results, and you can see here we have the bugs and then the test cases associated, and what the platform, the nodes, and so on. These are an example of if you expand on test issues, and this is you can see the reclassify buttons I mentioned earlier, so we can retrain the model if it make a mistakes. This is the view of setup issues, and something nice is that we also run another algorithm here, machine learning algorithm, to cluster setup failures. So it will automatically tell you, well, there were SIPs setup related failures, and these are these are them, and these are the associated frameworks that are showing those type of failures. So it kind of automatically do the clustering for you. It saves time as well. And then this is the potential hardware-software problems. This is where you will spend most of your time. Okay, I want to talk really quick about regressions. So we used to report a lot of false positive regressions, I guess. We have Checker here, he can tell you that that's the case. They stopped looking at our emails, regression emails. So we have to come up with a better way of reporting regression, right? Minimizing, when we say that something is a regression, it's truly a regression. So the first step was doing the classification, right? Because if a test case is failing because it's a setup issue or a test issue, well, that's a setup issue, test issue. It's not a problem with the software that we're testing. So it shouldn't be reported as a regression. And the other thing is, for something to be a regression, it has to pass before on that branch of, I don't know, if you're testing whatever is your branch, you have to have some history of executions on that branch so you can detect when something that used to work failed. So that's why we have these previous classifications and a new classification, and only if you have run that test on that branch before, then it goes into updating and comparing and seeing if it went from, it used to be classified as a problem or bug, and now it's classified as a pass, then it's reported as a fixed regression. And if it used to be classified as a pass and it moved to problem or bug, now this is a new classification. You see that here we don't have setup or test because they don't affect regressions. Essentially, whenever you run a test and it's classified as a setup or a test issue, it was a missed test. You didn't get any data whether it was a regression or not. All right. Conclusions. So, I mean, we just implemented the finished implementation and went into production last month. So we're still early, but we are already noticing that we are able to triage problems way faster because everything is in one single page and all aggregated, and it does the pre-classification, right? Before you will have to figure out, you have to click in the actual test and then figure out, it failed because, I don't know, there was an issue with TFTP. All that work is done by the tool and it's presented in a single page that is very fast. And we have also, I guess, saved a little bit of developer times by not notifying false regressions, because we are now able to truly detect more accurately when something is regressing based on the filters we have established before. The classification filter and then the regression filter that we run. So we have kind of two filters. In order for a failure to be classified as a regression, you have to pass these two filters. First, it has to be classified as a potential software problem, and then it has to pass the regression filter that it compares to previous classifications on that test case in that development branch. All right. So I'm, I think, 1 minute over. Future work. So we would like to see if we can apply this model to other products and operating systems. And yesterday, I think we were talking about potentially applying it to help with some of the LKFT testing, because we're interested in doing accurate reporting. And it's a difficult problem when you are trying to scale functional tests across a bunch of boards. You're running thousands of tests every day. If we don't have a system like this, it's kind of very resource intensive, right? So hopefully we can use it for LKFT. We haven't really experimented with different retrain weights. Right now we let it retrain with the default learning rate, but you can adjust certain parameters in the neural network to make it learn faster. So that's an area for exploration. Also, we can also do some tweaks in the vectorization and UI enhancements. Although we has implemented most of the UI stuff we want is looking, pretty complete, but there is always a new request, right? All right, some references, and that's all I have. I guess, yeah, any questions?
Can I access your test data? Or is it in-house?
Yeah, the test data is in-house. But the source, the implementation is...
I mean, we run same LTP and LTP, so if I found some bugs, I can just jump onto your website and search the data.
Yeah, but okay. But this is something important. I guess, are you talking about our model? The model we can share, but it's not going to be useful for you because we have to train the model based on the output because let's say, we want to see what kind of output we want to use for lava, right? Because remember, we use part of data, data coming from the device under test, but we also have some debug data coming from our framework. So we have to figure out what data of lava we want to use and then retrain the model. The good news is that train the model, I mean, again, simple model is like less than a day. So it's not a big deal. But I think at least based on this implementation, you have to train the model for each framework.
Yeah, thank you.
Any other questions? Yeah.
I have a lot of questions, but I'll just give you one. The tokenization you're doing with the test logs to get it down to 1024 inputs, what are you passing to that, and how does it decide which? Are you passing the entire test log from the start of the boot, and how does it? Because it seems like how it determines those 1,000 roughly tokens is critical. And
yeah. Excellent question. We did spend some time there. So right now, what we pass is we are not passing actually any of the bootloader logs or kernel execution, kernel booting logs. We don't pass that. Why? Because we have some way to detect failures at those stages, and we get that data from the kernel debug, from the framework debug, execution nodes. So in a couple of lines, we're able to say, oh, this failed because of that. So that way, we are saving all that. What we pass from the DUT output is what we call the test log, meaning if you're running LTP, is when we call LTP and whatever comes out, that's what we will put in the logs.
Of all of the LTP run, or just the specific test case that's failing? Do you have a way of parsing that specific section out, including the kernel messages during that section or something like that?
It will be whatever comes out after calling wrong LTP. So whatever is if your test case is running,
you're able to pass the entire LTP run in even for a specific test case failure, and it tokenizes it well enough to.
Yeah, it will tokenize. Of course, if there are some tokens that are very specific to, I don't know, an LTP test, they probably won't make it into the top 1024.
Wait, we need to talk more.
Yeah.
Thanks.
Yeah, I'm sure. I mean, it's hard to explain everything in 25 minutes, but at least this is an area where we have to take some time to try to tweak it in a way that it was efficient, just to keep the inputs small. Another possibility that I think is very applicable is to say, hey, forget it. We're going to use the top, 20,000 tokens. Let it be everything. That's another possibility. It's just more complexity into the model, more training, etc. But I mean, it could be a potential future work. That's what one of the things in the future work is the TF, IDF. This is a current implementation, but let's see. All right, I think we're 6 minutes over time, so we'll cut it here. Thanks for your time.